All right. Thank you all for being here on a Saturday, no less. We'll get started. I think we have a good group and we're ready to go. I hope you all have been enjoying the conference and the earlier sessions. Just first of all, a huge shout out to VISU for hosting us. I was at this conference last year, and the amount of polish and growth that I see year to year, this year compared to last year is just amazing. From what I know, it's mostly volunteer run. So thank you all for the efforts. And thank you for our facilitator today, Zohib. Awesome. So I'm going to start. I'll share my screen because there's a little presentation component to help guide our discussion before I dive into the demo. So I'm going to go ahead and share my screen. All right. So this is the session on continuously trainable AI as an alternative to deep learning. So in terms of the format, real quick, this presentation is to kind of walk through the problem and solution so that we're all in sync and we're all looking at the same thing when we're looking at the demo. The demo, I'll do it over screen share, and we will end with a discussion. But please, comments and questions welcome at any time. I think that's the beauty of an unconference. So let's make this as interactive as possible. Just jump in anytime you have questions or thoughts, especially we're such a small group. Let's do it. So a little bit about me to frame it as give you some context and where I'm coming from. I'm Ali from a company called AO Labs. Um, I'm a domain expert in weightless neural networks, which is the technique that underpins the demo I'll be showing you. I first met neural networks in 2012, right as the AI winter was thawing, and we had the first convolutional neural net or image recognition algorithms come out from places like NYU and Toronto, University of Toronto. And I had like it was a pleasure to meet Sion LeCun and Gary Marcus and a few other people like when they were really just kind of not famous yet. And since then, I've worked as an engineer and product person since my time at undergrad. But in 2018, I went back to my encounter with neural networks and went full time in AI research. And that's how I ended up at UC Berkeley as a researcher there. And so since 2023, I've been building out this tech as AO Labs. Really, this year, we're pushing it as a startup to put code out there with developers. So, but this is an AI safety conference, right? We're here to talk about AI safety, slightly more academic perhaps than at commercial applications. So the question I want to pose to you is, who trained your AI? Can you trust the trainer? How can you trust the trainer? That's the question that underpins this session. That was what we're talking about, training. And my proposition to you is that AI you can retrain or train yourself, you yourself, is liable to be more aligned and something that you at least can trust more. So the problem is with deep learning, the current paradigm we're in, the like 90% of AI is deep learning today. When people talk about AI, these are things like large language models and generative pre-trained transformers. And most AI in general is pre-trained by design. There's a pre-trained paradigm where you're benchmarking the algorithm against data and then deploying it for use. I'm curious, is that really clear to everyone when I say pre-trained, what that means? I'll be digging into it a little bit more, but I'm curious if anyone is completely unclear what pre-trained means. Like that's the P in GPT as a way to introduce it for those who don't know. So generative pre-trained transformer, it's really built into the architecture of deep learning. So digging into it a bit further, like what is pre-training? You usually have input and output, and you have a neural network or you have a model in the middle that's there to model input and output. It's there to learn the input-output function. But obviously there's more. Specifically, what I want to point out as more here is the reward or control function. When you're training an input-output system, the reward signal is implicit or explicit, but it's always provided from outside of the learning agent, right? So if you're training a large language model or a GPT, the reward signal is implicit in the training data you provide for that large model to set it up on the pre-training to get all the weights. If you've been watching the news, like Google's been trying to figure out how to use generative AI, and recently they had a thing where they were mislabeling Barack Obama as the first Muslim president. Um, that's just because it's just fed on the text it has, and probably has some text from some dubious sources. But the reward signal is just implicit, it's just trained on all that text. And even in reinforcement learning, the reward is maybe explicitly provided, but it's provided by a game score, it's provided from outside. So really digging deeper, we're talking about input output. There's a reward function, but the reward is coming from the output side, right? We're moving from few to many. So naturally, some information is lost. That's why we're in where we are today, because to try to get more input output learnings, we've created larger and larger networks, and our math can't keep up with it. So this becomes a black box where you might feed it an image and get a label, or you might feed it all these tokens and it predicts the next token. But it is where we are today. Even reinforcement learning, this is from the OpenAI reinforcement learning library, where you notice the environment variable is the reward is generated from the environment, right? So the reward is always outside of the agent's learning policy in a sense. I'll pause here real quick in case anybody has any questions or thoughts.
I guess I'd like to ask, by pre-training, do you kind of mean like the idea of transfer learning? So like we're training on some big corpus, that's not really related to the task per se, but it's kind of in the same domain. And then we start working on the task. Is that what you mean by that? Or do you mean like the more general practice of training on data and then applying to a task?
I mean the more general task of applying, the more general sense of
Hmm.
training on data and then applying a task. Um, Basically the step before transfer learning. Transfer learning is what people hope they can get from large models because they could be so general. So you might prompt it with a specific task, and then see if it learned that task from the prompt as a transfer. I believe that's what you're referring to.
Yeah.
Yeah, no, here when I'm talking about pre-training, I'm talking about like to get to the model to begin with, before your transfer learning, even all of those weights that are the model, that was pre-trained by decisions other people made around what data should go in it.
Okay. I think I'm on the same page. Thanks.
I have a question about this picture that you have here. I was wondering if you could elaborate more on the agent getting a reward from the environment. Like, could you, yeah, maybe give an example what that would look like?
Yeah, in the simplest sense, if you have a chess playing agent, an agent that's playing chess, or like the AlphaGo, the reinforcement learning neural network model that DeepMind built to beat the game of Go. In that case, you have the agent and all of its associated policies, and the environment is the game, and we can calculate the game score at every step. Because we can calculate the game score at every step, we can calculate that reward for the agent at every step. So the agent is unable to do that for itself or generalize beyond the game, right? So the hope of reinforcement learning is that they're able to generalize beyond the game, but that's been a bit lacking. We haven't heard of that AlphaGo model applied to other games, or rather applied to other domains.
Got it. Thank you.
Hello, I guess I have another question. In one of your slides, you're saying that if you can train your model yourself, then it could be more aligned. But how do you prevent misuse in that case? Because I think like any random person can be like, oh, I want like the AI to hack into computers, etc., or like kill people. Like how do you?
Yeah, great question. Great question. Where this specifically the demo I'm about to show you is AIs at a simpler level than natural language. So they're AIs that are like for personal applications or personal use cases. We're building up to agents that have the capacity to be continuously trained with natural language. We're not there yet with natural language. Those ones, yes, we'd have more deeper like security concerns or thus there. But we're not talking about like one large AGI that people would train on their own. We're talking about like, can we get smaller agents that people can train for their application? I think that'll be clearer to you, Emily, when I go through the rest of the presentation.
Sounds good. Thanks.
Thank you.
There's a question in the chat as well.
Is there a way to condense training data? Like if an individual was to personally train their model, I assume they wouldn't have enough compute to get a fully fleshed out model. That is a very good question. Yes, in the current paradigm, you need a lot of data, right? You need a lot of data to get any form of sensible result. So that's one of the reasons why continuous learning hasn't happened yet, because where are you going to get that continuous feedback loop? It's such small data, it's not really useful for the current techniques. We don't have a way to condense training data, but the demo I'm about to show you saves training data in a different way, and that actually is part of the part of why it's effective. And effectively, when you train a large model and then you have all the weights, that is already you're condensing all of the training data into those weights. So that's why the information is lost. So yeah, in our case, we try not to condense it. We try to keep it preserved at an agent level. And I think that'll be clearer too when I show you the demo. Was there another question in the chat? I think we're good. Awesome. I see your question there, Emily. We'll get to misuse again as well. So let's look at alternative. And this is where I'm going to get to the solution or one possible solution. Right. We're all working on software, so there's a lot of solutions. This is an alternative inspired by evolution. And so when you have a dog and you're training your dog, there's input, output, and reward as well. But in this case, if the input is fetch or sit, and the output is fetching or sitting, my dog is not sitting because of trying to get the best variance between input and output. My dog is sitting because of how I've rewarded it. So the reward is given to the dog as an input, and then in a sense, the dog self-labels to learn to do the right output for the right input to get rewarded. Contrasting that with what we said earlier, where the reward is passed through from the output side, you're going from few output to many, necessarily losing some information. That's why it's resolved into weights. This is a very different direction where we can actually save the input, output, and reward states of that agent as if you're preserving the conditioning history of an agent. And this is what happens this was inspired by the analogy with the dog here. In effect, classical conditioning. So if we go back to ML, first, is this sensible to people who asked questions earlier, perhaps?
Wait, so how do they know what the reward is? Like,
Well, that is a very good question, right? Like, so what we're looking at effectively is, can we build an AI system that determines its own reward in a sense, right? That calculates its own reward so that we don't have to do it for it, right? That's why we want to get to continuous training. If we're calculating the reward for it, we're back to standard reinforcement learning. So your question is very apt. That's why we've actually started with looking at much simpler organisms than the dog, right? This behavior, this classical conditioning behavior, it happens in humans too, right? And in fact, in some ways, it underpins our rational intelligence of words and language. But this behavior also exists in creatures much simpler than dogs. And we've built around those creatures as our reference designs because we have to be thoughtful about the shape of the agent so that it can calculate the reward by itself, right? We have to have the right number of input, output, and reward neurons for the particular application. I can show you that in the demo as well, because the demo is like we're talking about a dog here, and we obviously want to get to human level. And Emily, that was a little bit of your question. If the intelligence is so vast, how do you control it, right? We're trying to build up to human level intelligence that is so it can be relatable and more controllable, or something we can actually have a relationship with. But we have to start with simpler examples first. So the demo I'm going to show soon is even simpler than a human, way simpler than a human, even simpler than a dog, at a level of a creature like a clam. So if I just compare this to ML, like why does this matter? How is this different? It's easy to get lost in words. Maybe I'm using a reward in a different sense than the reinforcement learning language. But really what we're talking about is the dog can be continuously trained. It's explainable if I know how I rewarded it. If I know how I rewarded it, its behavior is somewhat explainable to me. Even if I don't know how it's rewarded, like I was to give you a dog from the wild, you still have a sense of its instincts that's grounding its learning mechanism. So it's continuous, it's explainable, and it's grounded. Instead of measuring how much it knows, we can be confident in how much it can learn. So, again, comparing this to ML, again, because the reinforcement learning is our closest cousin as a technique. Reinforcement learning, usually the reward, as I mentioned, or always the reward is calculated ex machina. It's an extrinsic reward. In our sense, to get to general intelligence that's grounded and trainable and trustable in a way that biological intelligence is, we have agents that calculate the reward on their own. So an intrinsic reward that drives their learning. So let me show you the demo now. That's where I want to go show the demo. Unless anybody had any questions first as I'm sharing my screen. And this demo is available on our website. You can visit it afterwards and play with it yourself. The code is also available for you to look at. So we talked about sorry, let me just fix my screen here. We talked about humans, which is what we're interested in, which is a little bit what drove Emily's question, like how is human level intelligence going to be? We talked about dogs as a thought experiment, comparing it to machine learning today. And I suggested to you that it's still a challenge to build an agent that can calculate its own reward. How do you do that? Someone asked. We have to be thoughtful about how we design the agent instead of just smashing it with data, right? So we've started with the simplest agent we can think of, and this is our hello world. Imagine an agent like a clam that has 3 inputs to 1 output. Can we get the system to learn to associate output with a particular input pattern? Like, say, can we get it to open more to chemical A as opposed to chemical B, or vice versa? And can we do that purely through input side training? We don't want to we don't want to give it a label, right? We want to get away from that. That's the pre-training world. So we have the input, we have the output, and we have reward here, which we've connected with food. So if you're with me on this toy example, I can show it to you working in action and we can extrapolate further. So we have this agent running in the background of this Streamlit app. Streamlit is awesome, by the way. If you've ever thought of coding with Python and doing front-end stuff, use Streamlit. So here we can show the clam agent that's living in the background of this browser. We can show it any input pattern, say food, chemical A and chemical B. And we can in this workbench, we can show that input pattern however many times as if it's like floating over it. And we can see how many times the agent responds by opening or closing. Now, in this case, the agent, I just did that 53 times and the agent didn't open at all, which is unsurprising because I've basically told it not to open. I pre-trained it to be closed in the absence of things. And you can see that here, it's still like it's not trained at all. It's still not opening. So let's try training it. Let's try training it to get the association to actually respond more to chemical A than chemical B. Let's do that experiment. So I'm going to pair chemical A and chemical B with food. I mean, I can do this in a simpler way, right? I can do this with a label. I can tell it like for chemical A, be open. That's like giving it a label effectively. But that's the boring pre-trained world. So what I'm going to show you is something different. I'm just going to add food as if I'm rewarding it. And in this case, it has an instinct for food. I've programmed it that food is the trigger for the learning function here. Now I'm going to pair chemical A and food also 53 times and see how it responds. In this case, we got an open rate of 96%. Now let's see what it learned, right? This is all subjective. Testing it is not an objective endeavor against a large data set. It's like reflexive with how you tested it. So I'm going to deactivate the instincts to make sure it's not learning anymore. Let me just check that. Sure, it's still opening quite a lot. I'm going to remove all the inputs and see what happens. So in this case, the clam didn't open at all, which is great. Let's introduce chemical B. I mean, you can make a guess about what you would expect it to behave, right? You can almost like anticipate its output. Cool. Didn't open at all. Unsurprising because I didn't pair this with food. But let's check chemical A. That opened 77% at the time. Cool. 86% at the time. Let's pair it with chemical B to see if that has any effect. It kind of does not. Awesome, as expected. What if we add food or I mean food, let's see how that pair works. Oh yeah, that it responds even more. And just food by itself responds similar to chemical A. And actually now if the instincts were on the whole time, it would be learning anytime food is present. So if chemical B and food are present, now it'll learn to associate chemical B with open, but less so than chemical A. I can run that as well. So in a sense, we can get it to learn any input pattern. We can get it to learn any input pattern by training it only on the input side. Now, somebody asked in the questions earlier about like, do we have to condense the training data or is there a way to condense it? In this case, the training data was the runs we just did, right? And the little like earlier when I told it to just be closed. So we actually save all of those states. We can save the input, output, and reward states relative to this agent. And that's like the conditioning history of the agent. That's actually how the algorithm works. It searches that conditioning history to give you a response instead of just being like a function that is responding like according to the weights. It'll use that lookup table of history to respond. So we can actually take a look at that history as well. This is the history of all of the neuronal activity. We only had 9 neurons for this agent. And we're also told why the neurons responded. So here, this was the pre-training I did, external label with the zeros. This is the pre-training I did in the beginning. That's why it was always closed. Otherwise, it would have been opening and closing randomly. But then this is where we just played with it in the beginning. And you'll see in here, it's going to show you where it's self-labeled. This is where it's self-labeled. So we have all this information. It's not lost as it would be usually. Usually you'd compress all of this information, the zeros and ones here. All this would be would be compressed into the weights. If you were to take that 9 by all of the states array and compress it into weights, just the 9 weights, that's what deep learning essentially does. Now, this is a very simple agent, very simple 3 inputs to 1 output, and 1 reward function, 1 reward neuron only. What happens if we have more? So my team and I actually were building up, using biological animals as reference designs because we can compare how this is classically conditioned to an animal at a certain level. And we're building up to more complicated reference designs. So, next up is a two-dimensional agent, a three-dimensional agent like a dog. Beyond that, we get closer and closer to an agent that would be able to take an input and then have its own understanding of words, the way a human or a dog has its own understanding of words in a way that's grounded, as opposed to AI like GPT, which has a lot of great words but still hallucinates. Yeah, I'll pause here for a few more questions and comments, or maybe anybody wants me to run anything else.
So is the main way this thing learns via like having some memory and then doing inference on its memory?
Effectively, yes. And it's kind of like a weird loop where it's preserved in its own memory, right? Because the memory is in the shape of it. So, but yes, it's searching that memory. Like that's one of the problems with the paradigm today as well, is like they don't have it does LLMs don't have built-in memory or context. That's why they struggle with reasoning. You can try to smash things in the context window, but that's not the same as having like your own words. Going back to the dog analogy, my dog has its own definition of sit relative to how I give it treats around that input output loop. And that definition of sit that my dog has is robust, and I can understand, I can manipulate its definition, I can understand its understanding. So yes, and this is the memory, Emily. Like, thank you for asking. We just digging a bit deeper. We can see even the memory at the neuronal level, right? Like we can query each neuron and look at its own individual lookup table. So this is the whole history of the agent, all of the activity. This is all of the activity of the agent. And then the neurons make up their own mini history from that. Obviously, there's going to be a lot of duplicates at the neuron level, so it's a smaller table for the neurons, which is why it's also more like this is how the part of the efficiency. Great question. Thank you, Emily.
There are other questions in the chat as well.
Ooh, please let me dig into that. I'm going to start from the top. So this is like agentic autonomous learning, I guess. Yes. Yes, Clary. We're trying to get to agentic autonomous learning in a way that is controllable by a human as the rewarder, right? In a way that we can relate to. I know that agentic and autonomous can be scary to say at an AI safety conference. We have this idea that, but like if you look at the current paradigm, OpenAI, for instance, is warning us about AGI, but clearly it's not agentic or autonomous yet. They're kind of making an assumption that agentic and autonomous will eventually appear somehow. I think that's contrary to evolution. I think agency and autonomy evolved slowly to more complicated forms. That's what I see at least. So I think we can get to safe agentic and autonomous learning by building bottom up. I hope I answered that question. Please let me know if you want to dig into it deeper. And then Kanad, if I'm getting this right, haven't you just moved the environment's information from the reward in traditional RL to something called instinct? Yes, effectively, yes. So instead, it's like labeling it once remove or giving a reward at once remove, right? And that's what we want. We want to be able to have even more automation in that sense by not directly specifying the reward, but specifying the method through which the agent will get its own reward, which is the instincts, effectively, right? You can imagine an agent that has an instinct for food and also an instinct for the converse. Maybe eventually it has some form of pain response. But also you can have then different reward neurons all around the agent connected to different neurons. And in that sense, you're not, it's a more distributed form of you doing that work.
And does moving the environmental signal from reward into instinct have any, does it address any of the other issues with RL, such as credit assignment and like does it do anything like what's the value of doing that? Do you get kind of emergent behavior as a result? Is like
I wouldn't say emergent behavior. I would say reliable behavior. Like there's an envelope of behavior we can rely on, right? Like, let me answer that question in two parts. I'll get to that reliable emergent behavior thing. In the beginning, you're asking like, what does it do? If you're doing this, no matter like, RL today is usually done with neural networks too. So this applies, right? But if you're calculating the reward and back propagating it, essentially back propagation, you are going to lose information to the weights. That's going to happen. So that's why you also have the black box problem. It sounds like you're a bit of a mathematician or in that vein, Kanad. And that's why you have the black box problem, because you end up with a parametric function like y equals mx plus b. It's a really long function because it's a really big network. And we have all the weights to give you the right output. So the function works. When it doesn't work, that's it. It's just a function. You can't go back. You can't go back and unpack that from the weights. So yeah, some interpretability or explainability is built into our approach by virtue of going this way through the transposition that you hit the nail on, which allows us to then save the full input-output state as a reward state. It can be saved piecemeal depending on if it's connected to all the neurons or some of the neurons. But it's saved, and that's what the agent then uses for its function. So when it gives you a function, when it gives you an output, that output can be traced if you have the configuration of the agent. If you know the configuration of the agent, like if you know how the input, output, and reward neurons are connected, you can do some math to trace back how that output was given from that lookup table.
super. Thank you very much.
Awesome. Thank you for that great question. Let me see here. It's not. I'm not familiar with Mamba. I have not. Emily, I'll get to your question about instinct too. That's awesome. But Mamba, I'm not familiar with Mamba. I'll have to take a look at it. But no, it's not. It's not based on Mamba. As far as I know, Mamba is still, from what it sounds like, it's still on top of deep learning. We're kind of like outside of deep learning. You can't really get away from back propagation or pre-training in deep learning, is my opinion. So we're like a weightless technique, weightless neural networks. It's an alternative to back propagation, so it's more like a machine learning. I'll look at Mamba. Thank you. Hi, Clary. That's awesome. Yes, so it's not completely autonomous. Yes, the human has to be in the loop to reward it. I mean, we can imagine some other instinct triggers. Like in this case, the instinct was food, and when the human passes food, we're building a Minecraft bot, and the Minecraft bot can be rewarded by the player. Whenever the player says good boy in the chat, the Minecraft bot saves the input and output, and it learns from that, right? So you're conditioning it like a dog, like good boy, good boy. But in that Minecraft bot, we've also used the pain signal from Minecraft as part of that learning loop, as an instinct. So you can get to you can build. It depends on how you build it, right? Depends on how you build. You can build those things. We still do it. It's hard to imagine how to build this architecture for a complicated agent. That's why we've really leaned on biology. And I can get into that a bit more if there's another question about that. But what are good resources to learn more about this sort of architecture? Oh, that's what we do, Emily. Please, we have docs, we have everything on our website. You can chat with us and drop in on our Discord. We're actually looking for contributors and collaborators at all levels. At all levels. A lot of our work is open source as well. And if you're looking for a job, let's come in. Come in with that intention as well. We're available for that. Yeah, Madan, I'm sorry I missed your presentation. I really was eager to be at your presentation. I'm sorry I missed it. I hope it was recorded. I did think that our thesis, our like topic session topics were similar. I think, like there's a huge difference between knowing something and understanding something. And in AI today, we have systems that know so much, but they don't really, you can't trust their understanding of what they know. It's like where does understanding come from and all of that? We're trying to grok that question, of course. Awesome. This is what I said earlier too. Like instead of how much it knows, like GPT or LLMs will make a mistake, and then people will be like, "Ha! It said Barack Hussein Obama is a Muslim. I mean, that means it's not generally intelligent or it's not smart." I mean, people make mistakes. That's not necessarily a smart thing or not smart thing. I think it's stupid just because I can't retrain it. I think it's stupid because I can't like fix its thought. That's why I think it's not smart. But so we want to move from how much it knows to how much it can learn, right? And I want how much it can learn to be reliable. If I go back a little bit to the dog, my dog is technically a general intelligence. They can fetch a ball, they can fetch a stick, they can sit, they can do all sorts of things. They're not gonna be a super intelligence. It's within a fixed envelope because they're programmed with their number of input, output, and reward in their neurology that I can rely on. That's where I see this getting. How is this neurosymbolic? Well, a symbolic AI is like the old AI where you like expert systems where you'd have a lot of opinions on how the world works, and you kind of try to put those rules into the AI or those symbols into the AI. And ever since then, people have been because that hasn't worked very well. Ever since then, the industry has moved towards neural AI or machine learning, specifically neural AI, which is like let's just smash it with data and search that data in fancier ways. We don't know, let's just search the data. The extreme version of it is transformers. Our approach is neurosymbolic. We're definitely doing neural networks, but you have to be careful about how you have the input, output, and reward neurons, how many of them and how they're connected. That's the symbolic approach. So the symbolism, the symbolic is in the architecture of the network, and then it's a neural approach on top. Hence neurosymbolic. Maybe now that we've told you about this, Emily, you'll begin to notice it a little bit elsewhere. There's a few other people working on like what's after deep learning or what's after backpropagation. Mamba plus forward forward. Interesting. Interesting. Yeah, forward forward is really interesting. Forward forward is definitely similar. Emily, we know those people. I mean, you can take a look at Symbolica and Liquid.ai and a few others, and there's researchers as well. I think we have a solid position and a few set of insights at AO Labs that are very different. So maybe but you can chat with us too, and I can share more resources, Emily. Mamba plus forward forward. That's awesome. Yeah, forward forward is really cool. I think forward forward is by Geoffrey Hinton. Geoffrey Hinton is like the father of backpropagation, which is this technique going back from output. And he's been looking at something called forward forward. And he literally says like we have to calculate the goodness differently. So it's pretty similar. Yeah, it's just people are working on what's next now. Claire, have you seen NVIDIA's Isaac model? Um, I saw their no, I'm not able to recall it. If you tell me a little bit more about it, we can talk about it. Those are some pretty great questions, guys. Thank you. So let me just round this out. If there's no more questions, this is great. I think we're great on time. I can move forward a little bit and show you. Ah, yeah, Emily, let's get into that just a teeny bit here. I'll use this as an example. It's just that with reward, you have to calculate it directly, right? Like there has to be somebody to calculate the reward. So usually that's why you need to pause the system, calculate the reward, and then back propagate or train it on that calculation. So that's why it's pre-trained. So I say instincts, and instincts are like how the reward is calculated by the agent, right? You can have a pain instinct, you can have a pleasure instinct, you can have it connected to half the neurons or all of the neurons. You can have it be triggered by different things. In the demo I showed, instinct was triggered by the food input, but you can have instincts triggered by by other stuff, by anything you need for your application. So in a sense, hopefully you can get to some sense where the user is rewarding it continuously, or its instinct is triggered. That's so we've distilled everything that you see in our demo, all of this stuff that I've learned about weightless neural networks, about this technique. That was Kanad's question, Emily. If you program the instinct, it is similar to reward, but you're still doing it at the once remove, right? It's like you're giving the agent the method to calculate its own instincts. Sorry, you're giving the agent the method, which is instincts, to calculate its own reward. NVIDIA's Isaac, I think you're. I'll get back to that, Claire. Thank you. Sorry, jumping around, but to stick with you, Emily. That's it's a subtle distinction. I think maybe you come from a reinforcement learning background. It's a subtle distinction. We tease it out more in our docs, and I'm happy to share more about instinct versus reward. In our code, though, in our code, in our website, you can access it. We've distilled everything that we've learned around weightless neural networks and this approach, where it's like one configuration file. You specify how many input, output, and reward neurons. Actually, let me just show you. Why am I talking? I can show you the architecture, Emily, of this agent. You're asking how do you program the reward and all that. I can show you the architecture of this agent. This was another demo that I had to show, but I think we're out of time. This is more of a commercial application demo. A demo of the CLAM, actually, a CLAM level agent, an agent at that level of simplicity, but applied to a network automation problem. But here is what I want to show you with, oops. But effectively, Emily, we have a library where we've distilled all of this. So you just specify input, output, and reward, how many neurons, and like what is the trigger for the reward neuron, for the instinct neuron, I mean. So you specify input, output, and reward through that way. And then it's one method to train or run that agent, right? Anytime you give it an input, it'll give you an output. Anytime you give it an input that has a reward or triggers it instincts, it'll learn in that way. Or you can even give it a label as I showed you in the demo. This is the architecture of the CLAM. We had 3 neurons, one for food, one for chemical A, and one for chemical B. And then we had one output variable. And then we connected the instinct neuron to the middle layer neurons and to the output neuron so they can learn relative to the input. And the input neuron has a very simple rule where if the mouth is open and food passed through, you feel pleasure, keep your mouth open. That's the only rule on the instinct. In this agent, you can specify the rule for your application. Yeah, this is where you can kind of play with the architecture to get a visual of it. But our code supports this. It's like one configuration file. In fact, it's one configuration file to build that agent and specify the instinct triggers. Awesome. I'm just gonna wrap up real quick. And we can leave time for you to catch your breath before the next presentation. Any other questions or thoughts or stuff? So about AO Labs. We're a startup building AGIs from the bottom up for trainable, relatable intelligence for every application. There's a layer of intelligence we're all missing out on when we can't retrain and train and take control of our own AI. And I say AGIs because this implies that we're responsible for little agents up to human level agents eventually. So it's not going to be one AGI, I don't think, that is going to be a super intelligent taking over the world. But we can build something better. And we're building more complicated biologically benchmarked reference designs. So I say biologically benchmarked because, again, we're not testing how much it knows, we're testing how much it can learn. So we can compare that against animals at that same level to say that we have an agent that can learn reliably at this level or we have a code base that that has this envelope of behavior. And that's how we think we can get to really reliable and useful commercial and consumer applications. What are some examples of those applications? I'm just going to give you some examples. You can build a recommender system that's trained per user, right? Like right now, when you go to Disney Plus, or you go to Netflix, or you go to YouTube, or heaven forbid, you go to Twitter, sorry, X, the recommendations are trying to sell you ads, or the recommendations are, even if they're not trying to sell you ads, they're recommending content to you based on comparing you to everyone else, because it's one large model that's trained on everyone's usage patterns. That's why you get filter bubble effects and people getting into weird content. We can build a recommender system that you train yourself like to fetch for you, right? I like to watch horror movies on Tuesday nights. Cybersecurity is another application from the developers we've talked to. Cybersecurity, usually there's always like these false positives or human attacks that escalate. So having something that can relearn is critical. And IoT devices. And I'll end with that. I'll show you a smarter interface. Imagine a light bulb. Imagine your lights at home. And maybe some of you have IoT devices like Nest or other smart home devices, and you've seen how smart they are. They're not that smart because they're, again, comparing you to other people. They're not learning your preferences because you're not the trainer. Imagine a light switch that's connected to a simple agent like a clam level agent. And based on your information, your context, it'll learn when to be open and closed, and you can retrain it through your interaction with the light switch. All right, so that could be a world where it's intuitive, really, to kind of just have your technology work for you instead of you work for it, right? Or instead of you're the product and the data for the technology, it's really just working for you. So that's it about AO Labs. I don't want to be selling. This was not that case, but I was trying to sell because I just want people to contribute. We're looking to build this out, especially if we're going bottom up. If like we can build more grounded AI by going bottom up, we can have AI that we can relate to and understand that it's behaving in this way. Bottom up means we got to do it with the community. So if any of these ideas spoke to you, please join our Discord. Maybe someone will drop that link. Let me drop that link in the chat. And please don't hesitate to ask any question or dig into it later. We also have open source that we do have contributors on. So if you want to get started, that's our Discord. I dropped it in the chat. Oh, awesome. I see a few more questions. I'll stick with them too, but let me just end this. Thank you all so much for the time. I appreciate it. I'm going to answer Claire's question. Last thought, do you think you can get an agent to autonomously learn ethics/emotional intelligence? You're actually, this is kind of, yeah, that I think we can, and I think we need to, right? I think we need to. Otherwise, it's like this. Sorry? Sorry, Daniel? I think that was a mistake. Yeah, I think we need to get to agents that can learn ethics and emotional intelligence because that's how we can trust them. Otherwise, it's going to be like the Tower of Babel, guys. We're going to end up building up this technological artifice. It's literally in words now, and we don't know how to program it or tweak it. Like Google is messing up with releasing AI reliably. So yeah, we definitely need to have some of that. I think it's necessary for two levels. It's necessary for us to be able to relate to the AI and to be able to actually trust it. But then I think emotional intelligence in that sense is necessary for the AI to be grounded, right? For the AI itself to be grounded. Like when my dog fetches my ball or sits when I say sit, they're not thinking of input output like optimization and doing statistics in their head. They just want the reward. They want to feel good, right? And so that's why their behavior is kind of like doesn't need a lot of training data. They're learning with respect to them and is grounded. I can reliably know how they're behaving with respect to how they feel. And another segue on that, like the hallucination word, be very careful with that, please. Hallucination in humans and animals is completely different than AI hallucination. When a human hallucinates, if you've ever been around someone who's mentally ill, they're completely convinced of their own reality. right? So there's a sense of truth that humans and animals have. AI doesn't even have a sense of truth. So when it hallucinates, it's just wrong answer relative to you, but it's not even a hallucination. It's not even wrong. It's really scary actually, because people can anthropomorphize it in the wrong way. Yeah. Yeah. Non-college and hallucination in a human, in a sense, is like a distortion of their own um, perception with their own sense of truth, right? They still have a sense of truth, so that's why they're convinced of their hallucination, but they're obviously like distorted perception-wise. So that's the difference a little bit to dig deeper into that. Awesome. I really appreciate all of your questions, everyone. Thank you so much. I really hope you enjoyed this presentation as much as I enjoyed giving it. Again, huge shout out to the VAISU team. I really hope there's a third conference, and I hope to see you at the third conference as well. Awesome. I'll stick around for whatever until like I jump to the next session myself. But thank you all so much for being here.